the nice example that illustrates this is the n queens problem. Let's think of 8 queens, but we can actually 8 queens. So what is the problem? You are given a chessboard 8 cross 8, and you are supposed to place queens on the chessboard such that no queen attacks each other, no two queens attack each other. Okay, so suppose you place the first queen here, then let's just draw some. Suppose you place the first queen here, then you cannot place the queen in the next row either here or here, so you have to place it here. And then now for the third queen, where can you place it? You cannot place it here or here, because this queen attacks this queen attacks that, this queen attacks this, this queen attacks this, this queen attacks this. So you have to actually go all the way here. Okay, so here is one queen, here is another queen, here is a third queen. Okay, and I have not drawn 8 really. 1, 2, 3, 4, 5, 6, 7. Let's extend it to one more. 1, 2, 3, 4, 5, 6. And now for the next queen, you will see that you will have to place it. You cannot place it here or here or here. You cannot place it here either, because this queen attacks it. You can place it there. Okay. And for the next queen, you try to place it here. Maybe you can place it there, because 1, 2, 3, 4, 5 that attacks this. Yeah, you can place it here. On the next queen, you cannot place it in any of these columns. You have to place it here, but you can't place it there because this queen attacks that. Okay, so you have to actually go here, but then you have to check whether some other queen, you cannot place it here because this attacks that. You cannot place it here because this attacks it. So at this point, you will realize that, oh, placing this queen here was a mistake. So maybe I should place it elsewhere, and you will try to place it somewhere here, and then try to see if you can extend this. Okay, so this is the point. So you try to place your queen somewhere, and then if you cannot place it, then you will erase that and go back and place it elsewhere. But maybe at some point of time later, once you tried this, maybe you went all the way, you placed some queens here, 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 etc., and then you find out that something is wrong. Then you will have to backtrack all the way back and even erase this. Okay, you should even erase this. Okay, so this is the point. So you try to build a solution. At some point you realize that a complete solution is not possible following this path, so you backtrack. And you can see how this is related to graphs, because initially you start out with it is tree rather than a graph, but yeah, so initially you start out with the empty solution. There are lots of ways to extend this. And from there are lots of ways to extend it again. And some of these ways of extending two different things might collapse to the same. Yeah. So in general, it's what is called a directed acyclic graph. And you take these paths, and so at every path you will try to see if something is consistent or not. So you will mark it as green or red based on whether it's consistent or not. The moment you discover that something is red, you will go back and so what is the problem? So you don't explore this graph in one shot. Rather, you will go down a path. So you will try the first extension, try this extension, try that extension, etc., till you reach a point where you either have a solution or you will realize that there is no possible way to complete this and get a solution. So you will backtrack. So you will go back here and then try the next solution, the next possible extension. And maybe here also there is a problem. So you will go back and maybe now you have exhausted all possible extensions at this level. So you will go back here. Okay. So this thing itself you will give up, and then you will go back and try that other extension there. Okay. So this is really the problem, and you generally will have to backtrack. Okay. Okay, so now let's get to the details of, okay, so what are we trying to do? We are trying to somehow write a nice program in Haskell where we don't have to go through all these intricacies of backtracking, okay. So we want to write a simple program, a direct program, but it should somehow be efficient, but the programmer shouldn't face much difficulty, okay. Let's see how to do this, okay. But before that, let's just explore, let's just concretize what we mean by attack, etc., etc. So two queens attack each other if they are on the same row, column or diagonal, okay, that much is clear. There are n queens, n rows and n columns, exactly one queen in each row and each column, yeah. So this is needed because if on the same row you put two columns, clearly they attack each other. If two different rows have queens on the same columns, definitely they attack each other. So since there is exactly one queen in each row and column, ideally speaking, you would have to represent the position of the queen as a pair of coordinates, row comma column, but we needn't, because we can represent the thing as a list where the first position tells the column in row 1 that the queen will occupy. Second, so if I write something like 0, 2, 4, 1, 3, 7, 5, 6. Yeah, this means that in there is a queen in row 0, column 0, row 2, row 1, column 2. Remember, we are counting numbers from 0, not 1. Okay, so there are, if you think of it as an 8 bar 8, 8 cross 8 board, then you have 8, then you have rows numbered 0, 1, 2, 3, 4, 5, 6, 7, and columns numbered 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that's what this means, and there is a queen in row 2, column 4, row 3, column 1, row 4, column 3, row 5, column 7, row 6, column 5, and row 7, column 6. Okay, this is what it means. Okay, and you can actually draw out the picture in the on a board if you have, and then you can figure out whether this is the correct configuration or not by trying to see if some two queens attack each other. Okay, here is the solution that we want to try. Place the first queen somewhere in row n-1. We will start with the top row. For each lower row, place a queen at the leftmost square that is not attacked by any of the earlier queens. So we will start here and we will place the first queen somewhere in row n-1. I will place it in column 0. So this is 7, 6, 5, 4, 3, 2, 1, 0. And I have 0. Let me choose a different color for the placement. So I'll first place the queen here, then I'll place the, for row 6 I will place the queen at the leftmost square not attacked by the earlier queen. So this and that are attacked by that queen, so I will place it here, and when I come to row 5, this is attacked by that queen, this is attacked by this queen, this is attacked by this queen, this is attacked by this queen. I can choose this. When it comes to row 4, I will choose the leftmost, and this is the leftmost. Here this queen cannot attack this queen cannot attack this, and that queen cannot attack this. When I come to row 3, these three things are ruled out. This is ruled out because, why is this ruled out? This is not ruled out, right? Yeah, I can place it here. When it comes to row 2, then these three, this is ruled out. This is ruled out because of that, because this queen is in that column. This is ruled out, this is ruled out, this is ruled out, this is ruled out. I have to go here, but I cannot go here because that's on the diagonal. So I have to go here, but this is on this diagonal. So I have to go here, but that is on this diagonal. Okay. So you see that if I do this, I cannot extend it in any manner to include row 2. So what I have to do is I have to erase my choice for row 3 I have to erase my choice for row 3 and then choose another one, and the next one where I won't have any attack will be somewhere here, okay, and then I have to continue like this, okay. That's my heuristic. If the current configuration cannot be extended to n queens, try the next available square, okay. So this is what I want to do. If you run out of squares on this row, try another square in the previous row. So you have to backtrack. This is the backtracking. Okay, so now let's actually see the solution in Haskell. Okay, so any placement of queens on the board I will call a configuration, and as I told you, I can represent a configuration of 8 queens or n queens on the board by a list of integers based on the position. So, right, so a configuration is a list of length n minus I, where 0 is less than or equal to I less than or equal to n, because my original aim is to place I should say less than n, I suppose. No, yeah, length n minus I, that's correct. So my configuration can either be length 0 or length n or anything in between, okay. So store column numbers of each queens in row I to n minus 1, okay. At any point of time, if I say 2, 3, 5, then it means queen is in row 5 column 2, row 6 column 3, row 7 column 5, because I want to always represent, I am always placing queens from top to bottom. So if I have a list of length 3, then I am saying where the queen is placed here, 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 somewhere, okay, on these 3 rows, okay. And yeah, so this is the point. So my list will be in configuration at index 0, at index 2, etc. till n minus I, okay. So fine. So configuration, the configuration is a list, conf is a list, conf at position j corresponds to the row n minus length of conf plus j. This you can work out, okay, from the slides. So adding a new queen in row I minus 1 corresponds to adding an element at the head of conf, okay. So you want to add an element at the head of conf. Now you have to so here is an example configuration for 8 queens. So here it is 0, 2, 4, 6, 1, 3, 5. There are 7 queens here, and I claim that it cannot be extended because you can draw the picture. This is 0, 1, 2, 3, 4, 5, 6, 7. Yeah, 0, 1, 2, 3, 4, 5, 6, 7. And I am saying my current configuration is, there is a queen here, there is a queen here, there is a, so let me just draw there is a queen here, 6 is this, there is a queen here, there is a queen here, there is a queen here, and there is a queen here, and you can actually verify that this configuration cannot be extended any further, okay. So draw out the configuration and check that. Okay, so now we have to program all this. It's one thing to draw it out and then visually see it and check that it is the correct configuration or not, and even that works only for 8 cross 8 chessboard. We are talking about generalizing it to n cross n, where n could be anything. So, okay, so suppose you are given a configuration which is valid and I want to extend it by 1. Okay, how do you do? extend by 1 n conf gives all ways of extending conf, where this n is the n in the n cross n puzzle, the total number of which is equal to the total number of columns, which is equal to the total number of queens. Okay, that is n. Okay, for the n cross n puzzle, if I am given this configuration, how do I extend it by one by adding one more queen? Remember, we are imagining that we are building the solution from top row to below, and adding one more queen would be to add one element to the head of the list that we have. Okay. So, new queen is a column from 0 to n minus 1. So, the new queen should not be in the same column as an earlier queen, should not be in the same diagonal or anti-diagonal as an earlier queen, right. So, same column as an earlier queen you can check, because if it is in the same column as an earlier queen, then this would be a number that is already there in the list. If it is in the same diagonal, let us just do some simple math. If I have a queen here and if it is in the same diagonal, then if you look at it, this is some row number and this is some column number. If the same diagonal repeats, what is the element in row plus 1, r plus 1, which has the which is on the same diagonal? It will be r plus 1 c plus 1. It will be r plus 2 c plus 2, and so on, right. So, what do you need to check? So, we need to check whether it is on the same diagonal. Similarly, we need to check whether it is on the same anti-diagonal. So, remember that if you recall from your high school the definition of slope, the slope of this is r equals c, and here for this, so the thing in the next thing will be r plus 1 c minus 1, r plus 2 c minus 2, etc. So, it will be yeah, so here the slope will be x equal to y, here the slope will be x plus y equals r plus c. Okay, that is the thing, because the sum stays constant. So, that is all you need to check. Okay. So, and finally, we do one trick, which is that it does not matter if I am considering n rows. If I just want to check the validity of adding a new move, it does not matter if I am if I have rows n minus 1 to n minus r plus 1, and then I am adding this thing, or I could just translate it all the way down and the same attack pattern continues, the notion of diagonal, anti-diagonal, etc. is the same, except the formulas become simpler. Okay. So, when I try to extend a configuration by adding something at the head, I will imagine as if I have something from I have filled something from row 1 to row 5, let us say, and I am adding something in row 0. Okay. So, that is what I will do. Okay. So, extend by 1 of conf is just c colon conf, where c comes from 0 to n minus 1, and it is safe to add c to the conf, where safe just means c is not an element of j such that ij is in occupied cells. C is not an element of j minus I such that so remember I am having 0 comma c. Okay. And if everything on the same anti-diagonal, on the same diagonal, this will satisfy the equation x equal to yeah. So, this will satisfy the equation y equals x plus c. This will satisfy the equation y plus x equal to c on this anti-diagonal. So, I am just checking that. Okay. To say that y equals x plus c is nothing but saying that c equals y minus x. To say that this is just to say that c equals y plus x. So, that is what I am checking. Okay. So, but how do I compute the occupied cells? Occupied cells are nothing. I will just think of this configuration that I am given as from cell 1 to whatever. So, I just zip the current configuration. The current configuration is a list of columns. I'll zip it with 1 dot dot. So that will give me pairs, okay. And using this I can compute when it is safe to extend by one configuration. So this is a lot of detail about the 7 queens and how you attack, etc. But now comes the nice thing about Haskell and laziness and so on. Yeah, so 0 C is the position of the new queen. It will clash with an existing queen at position ij if C equals j, meaning queens are in the same column, or C minus 0 is j minus I, meaning queens are in the same diagonal, or C plus 0 is j plus I, meaning they are in the same anti-diagonal. So all these checks you can do. Now comes the thing. So I now have a given configuration and I want to find out all ways in which I can extend this configuration. So firstly, I will say if my configuration is already of length n, this means it's a completed configuration, it's a complete solution. So all I need to do is I need to provide a list of configurations. I will just provide a singleton list of singleton list consisting of this configuration. Otherwise, what I will do is I will extend this configuration by 1. Okay, and no, I'll have to extend the configuration by 1, but I have one configuration, I will extend it by one more row, okay, and I need to now continue to do this, okay. It's like the previous solution with my iterate. What I'm saying is, oh, don't stop with this, try to extend it once more, try to extend all these things once more, try to extend these once more, try to extend these once more, and you will get something. You try to extend these once more till you hit the base case where your length is already n, okay. At this point you will stop. So and then what I am trying to do is I am concatenating all these solutions. I am creating one list consisting of all these solutions, okay, which is why I have the concat map, okay, fine. So that's my solution. Now if I want to solve the n queens problem, I just want to say start with the empty solution. There is no solution to begin with, and just keep extending it, or think of it as the empty solution and keep extending it till you reach a configuration with n queens, okay. And this itself is an infinite, potentially long or infinite list. But what I do is I will just pick the first one, queens I of 0, that is my queens 1. What I am doing is I am picking the first solution of all. So what the way I have described the algorithm, I am saying start with 1, in one shot extend the solution by, in one shot find all extensions by 1 move, then in one shot find all extensions by 2 moves, etc., etc. But in reality, Haskell, because it is lazy and because you have written this bang bang 0, which is to say that give me the first solution, it won't completely explore this tree. It will just try to explore the tree as much as is necessary. It might try to go down this path, maybe it gets stuck, so it will backtrack and it will go take another path, etc. So the point is, you wrote a program in an extremely simple manner, in the manner of what is called breadth first search. Where you said find all extensions by 1 move, find all extensions by 1 more move, find all extensions by 1 more move, etc. But Haskell will actually execute it in depth first search. Breadth first search is your program. Depth first search is Haskell's implementation of it. Right? So, and you actually get a solution, and you will get a solution very, very quickly. I will demonstrate it for you in a bit. So, to summarize, infinite lists are a very useful way to think about search problems. Instead of backtracking, instead of using backtracking as part of your program, you iteratively generate all valid solutions up to a desired depth. This is very simple to program. Lazy evaluation converts inefficient breadth first search to depth first evaluation of the leftmost solution. Okay, and this is the summary, and this is very powerful already, as you can see. So that concludes this lecture. I shall now just show you how this works in VS Code, and I will stop the lecture. As you can see, I have programmed all the things that I explained earlier in this, right? And so let's actually try this. Queens 1 of 8 is what I should try. And you see how quickly you get a solution. If you want, you can actually draw this out and figure out that this is a solution. And notice importantly that yeah, I made some minor modifications in the code here just for some more improvements, but you see that you can get some very quick these things. In fact, you can actually search for how many solutions there are. Okay, Queen's 8 of, let's say, the 25th solution, you get something else. Okay, Queen's 8 of 54th solution, you get something else. Okay, you can try to explore various kinds of solutions also for this. I could just say Queen's 8. This won't terminate, but it will Queens of 8, I should say. Okay, it does terminate. Okay, so you actually see that it produces this list. I could do, and this is not just 8, I could do Queens 10 also. If you can imagine a 10 cross 10 chessboard with 10 queens, right? This is of course much longer, but you can actually get all solutions. Okay, fine. I hope this lecture was informative, and you appreciate and I hope you appreciate the power of Haskell's laziness. Okay, thank you. I'll resume with another topic in the next lecture. Thank you.